Chapter 6 and 11, slides 8 to 37. Now that we understand how the radical halogenation mechanism works, let's go back and look at this more complicated example, starting with propane instead of methane. And what you'll see is that if you consider methane, and let's say we react it with bromine and light, you'll notice that there's a possible mixture of constitutional isomers that we can get. We could get 2 bromopropane or 1 bromopropane. Now, according to the mechanism, you saw that HBr is a byproduct for this reaction, so we're going to see that no matter what. But I wanted to point out that a more complicated example gives us the possibility of reacting the bromine at 2 different positions. Now, in order to consider this reaction, we're going to look at energy diagrams and use them to understand how to determine product mixtures. So first question is, why do we get these mixtures of products? And is there a way to modify the reaction to perhaps favor one product specifically? Are the observed products formed because they're the most stable products possible? This is something that, as you're going to see, we're going to call the study of thermodynamics. Or are the products favored because they have formed fastest? And this is called kinetics. Now, formally, definitions, thermodynamics is something that we're already familiar with. It's the study of energy changes that accompany chemical and physical transformations. Using thermodynamics, we can compare the stabilities of reactants, starting materials, and products, and predict which compounds are favored in a system at equilibrium. Well, we've been doing systems at equilibrium in the acid-base chapter. Okay, so you guys are no strangers to looking at an acid reacting with a base in equilibrium and looking at its conjugate base plus the conjugate acid, right? And the sodium is the counter ion. And you guys knew that the pKa of water was 15.7, and you look up the pKa of the acid on the left and it's about 5. The weaker acid is water, and so you were saying that equilibrium favors the weaker acid. Another way to look at it is that equilibrium favored the more stable conjugate base. So you're looking at a system at equilibrium. You're looking at the starting materials. The starting materials are in yellow. The products are in blue. And you weren't looking at the journey. You were looking at the starting point and the destination. And you were determining qualitatively, you were making determinations of stability in this equilibrium. And then you were looking at which side would be more favored. Okay, and it was all based on stability. You were looking at the conjugate base stability using REO. So the bottom line is, when you're considering thermodynamic reactions, what you need to be asking yourself is, what is more stable? Right? That is the key to thermodynamics. You're looking at the stability of the starting point, of the finishing point, perhaps of some intermediates along the way. You're just looking at their energy levels relative to each other and which one is lower in energy, thus more stable. Kinetics is what's happening on the journey. So remember when we had a map, right, of the United States, and we started at point A and we ended at point B. Understanding where you are and where you're going, right, from A to B, that's just thermodynamics, relative stabilities. However, if you consider the journey, the path to get there, right, that is like studying the kinetics, right? You can take the northern route, the middle route, the southern route. how long it takes you, how fast the reaction occurs, right, is the study of kinetics. It's the field of chemistry that deals with the rates of chemical reactions. Understand that in all three of these scenarios, they were all going from A to B, but they could have different rates, right? You could, depending upon which route you take. So kinetics is, I want you to really think, how fast? Thermodynamics, what's more stable, right? Stability for thermodynamics and how fast for kinetics. Okay, so let's go back to our flashcard. We've looked at methane halogenation using a radical mechanism. One of the things that is determined by rate is the reagent. And in this case, we've used chlorine. You've seen me use bromine. It's important to note that for this radical halogenation, one of the things that is in consideration for kinetics is the reagent. And what we'll find is that for fluorine, it's way too reactive. If you put fluorine and light, way too reactive. Iodine, it is not reactive enough with the light. So to get things moving, for the iodide radical to propagate. So what you're going to see is that for radical halogenation, the sweet spot is right in between there with chlorine and bromine. Thus, you're only going to see me giving you chlorine or bromine when running a radical halogenation reaction for an alkane. I just wanted you to be aware of that. Okay, let's use our methane radical halogenation as an example reaction, since it's, a great first start to you guys learning some organic chemistry. We've got a carbon, the simplest carbon, right? Methane, and we're chlorinating it. We're changing it into something else. Bonds were being broken and bonds were being formed. Now that we have the context for a given reaction, I want to now cover energy maps or reaction coordinate diagrams. These are, I like calling them energy maps because they make me think about these maps of, starting at A and going to B, or starting from B and going to A. It's a map, right? So I want you to think of it that way. And we're going to dissect all of the information that is packed into this energy coordinate diagram. The first thing I want to talk about are transition states. Transition states are the high energy points that you're seeing on this diagram. So for this reaction, you can see that there are two humps, okay, of high energy. Notice that energy is on the y-axis. On the x-axis is our our reaction coordinate. I want you to be very cognizant of the fact that this is not time, okay? If I meant to say hours, minutes, whatever time, I would have put time in the x-coordinate. This is just the coordinate. Think back to our map, okay? As you move from B to A, if B was our starting point and we're traveling to A, this is our coordinate, right, on the map. It's a map. It doesn't tell us how long it's going to take to go from B to A. It's just showing that I'm starting here and I'm ending there. As the reaction or as my travels progress, I'm moving, right, from here to there. So it's the same type of concept in an energy coordinate diagram. It is not a time scale on the x-axis. It's from start to finish arbitrarily. I could have drawn, right? If I have an energy coordinate diagram from start to finish, and I go like this, versus from start to finish, and I go like this, because one is longer than the other doesn't mean that it took longer time. Maybe I had to draw it in a smaller space. Okay, so I just want to really emphasize that it is not a function of time. It's just showing you that from the start, you're here. So here's your starting point. Far to the left. Notice that we're starting with CH4 and the chlorine radical. That's where we're at energy-wise. By the end, our products will be over to the right. You can see the methylchlorine, the methyl chloride, and the chlorine radical. In the middle, we're going to form a CH3 radical. Okay, so the transition states are those high points, those high energy points that you have to climb, that you have to give the system to get to the next energy, whether it's higher or lower. We can liken this to a hiker on a map, right? So here's our map coordinate. Not time, just map coordinate. It's showing the starting point, it's showing the finish point, and it's showing some stop in the middle, okay? And these are the hills that have to be climbed, right? So these high points are called transition states. And there are 2 high points. So how many transition states does the reaction for the chlorination of methane have? Well, according to the energy diagram, it says that there are 2 transition states. Intermediates. Intermediates are short-lived species that are never present. Okay, so these are actually observable things. They're short-lived, but they are there for long enough for us to detect. As opposed to a transition state, which are these high energy states in molecular collisions, we don't have the means of actually capturing the collision at that high energy point. So there are energies we know we need to overcome, but we don't have, we can't show them actually happening. They're unstable, and we can't isolate them and say, hey, look, here's a transition state. No, they're very fleeting. But intermediates are actually short-lived species that we can detect, but they're not there in high concentrations because they're so reactive and high energy, they react quickly and form the next thing. How do we know when we have an intermediate? Well, they're typically charged. So if you're doing the mechanism, and along the way of the mechanism, you form a carbocation or an anion or a radical along the way, then you're going to see an intermediate. And if you check out the energy coordinate diagram for the methane, if you recall the mechanism, right, we formed a CH3 radical at one point. So on our carbon-based species, it went from neutral CH4, starting material, to neutral CH3Cl, product. And there was this intermediate state in the mechanism where CH3 radical had formed. That's a high energy intermediate. And you can see that it's higher in energy than both the starting material and the product, and is given the spot on the energy coordinate diagram. So if we look at the energy coordinate diagram or the mechanism, we can see how many intermediates this reaction has. It has 1 intermediate. And that's represented in my hiker's map diagram as the base camp high up in the elevation, right? You're not going to stay there very long, but you need to stop there along the way, maybe get some rest, and then keep going. Okay? So this is unique. The energy coordinate diagram is unique to different reactions. It's all dependent upon the kinetics of the reaction, how much energy needs to be expended, put into the system in order to get the chemistry to happen. Now, any time that you have a reaction, bonds making, bond breaking, there's going to be a transition state. If I'm sitting on the couch and I want to go to the kitchen, right? Final destination is the kitchen. I'm starting at the couch. Unfortunately, I can't snap my fingers and just beam myself there. There has to be a transition of me getting up, expending some energy, and going to the kitchen. So if you're doing chemistry and sigma, bonds are breaking and making, then you're going to have a transition state. There's not one chemical reaction out there that doesn't have to overcome some energy as atoms approach one another and their electron clouds repel one another until they find that sweet spot and react. you're going to have a high energy state, so a transition state, as you transition from something to something else. You won't always have an intermediate. So energy coordinate diagrams are unique for each individual chemical reaction. How about rate limiting step? Well, this is also given to us in the energy coordinate diagram. How do I know? Well, it's the highest energy step of a multi-step reaction, or the bottleneck. So if I had my starting material, right, there's my methane, and I see that from the methane to the CH3 radical, that energy is the highest, right? It's not about the difference. We're going to talk about activation energy in a minute. We're only comparing the peaks to one another. Whichever is the highest peak is going to be the rate determining step. So you just sort of step back and you look at the landscape, and whatever the highest mountain is, because that one has the least oxygen on it, right? If you're hiking, this mountain is going to cause you the toughest time because it's so elevated up there, right? So if elevation was on our y-axis, getting up over that peak is going to be the toughest, right? And most exertion. So whichever reaction or whichever transition state overall for the whole reaction requires the most energy, doesn't matter where you started, that one's typically the rate limiting step. So if I were to ask you on an exam, which is the rate limiting step for this reaction, and I gave you the energy coordinate diagram, you either would choose from starting material to intermediate, from starting material to intermediate, that's this path, or you'd choose from intermediate to product, from intermediate to product, and that's this path. And whichever one has the highest one, which we just determined was from starting material to intermediate, that hump is higher, then starting material to intermediate is going to be the rate limiting step. You have to be given the energy diagram to answer the question. You will not be able to draw these transition state energies and such just by pulling things out of the sky. You have to be given information. All of the information about the energy levels of transition states relative to intermediates and all of that, those have to be given to you, and they're determined experimentally. So don't think that you can suddenly just derive an energy coordinate diagram because you know the mechanism. No, you have to be given information experimentally in order to map out what this looks like. How about a catalyst? Well, a catalyst is a reagent that's added that helps bring the energy level of a transition state down, therefore lowering the activation energy to get to the products. So understand that when you catalyze a reaction, you're not changing the initial energies of the products and the starting materials and the intermediates. Those stay exactly the same. Okay, so I have down here the hiker, no catalyst, starts here, ends here, has an intermediate, base camp. Okay, if I add a catalyst, I want you to notice that all of these energies are exactly the same. So what's different? What's different is that a catalyst lowers the mountain. So notice that this difference, there's a difference right here. That mountain is lower, and there is a difference, right? We've lowered the mountain. So it's not as high of a peak to climb anymore, and this makes it so much easier. So that's what a catalyst is doing. You're not changing the energies of your starting materials and your products or anything like that. You're simply lowering the energy that you need to climb, that's required in order to get over the hump and get to the next intermediate or product. Okay, a little bit more on thermodynamics. Now that we have mapped out what is kind of packed into the energy diagram, we have to understand how to read the levels. What does it mean when you start higher in energy and end lower in energy? Or start high in energy and go even higher in energy to an intermediate? What does all of that mean? Okay, what about the lines? How do we draw these lines from, of the transition states, and what does that all mean? So in order to do that, we're going to dive a little deeper into thermodynamics and kinetics ultimately. Now, thermodynamics, again, describes the properties of a system at equilibrium, right? So this is a little bit of a review from general chemistry. Remember, if the products are in greater concentration at equilibrium, meaning the products are favored, they're more stable than the reactants, let's look at the equation for KEQ, right? So here is a reaction. The products are C and D. And so for KEQ, if the concentration of products divided by the concentration of the reactants, if we're given that, and if we know that the products are favored, that means this will be a bigger number, bigger concentration, right? So if you put a big number over a little number, you're going to get something that is greater than 1. It's only when you have a little number divided by a big number that you start getting numbers less than 1. How can this understanding be applied to acids and conjugate bases? Well, let's think about it, right? When we had an acid plus a base in equilibrium, and you had the conjugate acid plus the conjugate base, if the reaction favored the products, then your KEQ would be greater than 1. If the reaction favored the starting materials, then your KEQ would be less than 1. So if you have an equilibrium, I want you to see what I'm trying to do right now, since KEQ is right, where I'm trying to get back to this energy diagram here, right? Here's your energy diagram. We don't see any KEQs anywhere. So what I'm trying to do now is relate what you've learned in Gen Chem with equilibrium constant to energy. So let's remember Gibbs free energy. Delta G, energy, the change in energy, is equal to negative RT natural log of KEQ. So there is a relationship between KEQ and delta G. We're not going to be doing these calculations in class. You guys spent all of Gen Chem doing stuff like this. I'm just reminding you that there is a relationship between KEQ and delta G. And it's a negative relationship, meaning this whole number here becomes negative. So if delta G is positive, then KEQ would be negative. And vice versa. If KEQ is positive, then delta G is negative because of the Gibbs free energy equation. You got to remember that there is a relationship there. And because it's a natural log, right, take a look at what happens at, let's say you have a KEQ of 1.2, your delta G is going to be negative 0.11. Okay, it makes the positive negative make sense. But notice that what happens is that for every 1.36 kilocalories per mole of free energy, so we're kind of bumping this up, right? Not very much. I'm not bumping up the energy very much. But look what happens to the KEQ, right? The equilibrium constant. Because of the relationship in Gibbs free energy between delta G and K, not just with the plus and minus, but because of the natural log, we see a massive jump in the number of the KEQ. So look what happens in an equilibrium as you go up and up and up in value from delta G of, say, negative 0.11 to negative 7.7. Doesn't seem like a huge leap from negative 0.11 to negative 7.77, but look at the leap you make in favoring starting material to product from 54% to 99.99%. That's huge, okay? So I want you to recognize that when products are favored, KEQ is greater than 1, the delta G will be negative, and changes in delta G make a really big difference in the percentage you end up seeing. Okay, so another thing that is going to come in handy that I want you to remember from your Gen Chem days is Le Chatelier's principle. So that when you're working in equilibrium and you have, starting materials and products, I want you to remember what you can do to favor or shift the equilibrium from one side to the other. This is something that as we learn more chemistry, and if we're under thermodynamic or equilibrium conditions, then when you're running a reaction in the lab and you're not getting the product distribution that you want, you have the power in the lab to make some changes. And if you understand that you're under an equilibrium, then you can use Le Chatelier's principle to your advantage. Let's say you are having trouble getting your C plus D products. What could you do to shift the reaction more to the right? Well, if you said I could increase A concentration, you would be correct. If you said increase B concentration, you would also be correct. That's one way to do it. You could increase the concentrations of your starting material so as to shift the equilibrium to make more C and D. Also, let's say D was the one that you really, really, really wanted. Sometimes what happens is that one of them is the one that you're really interested in, and the other one might be some, liquid byproduct. And maybe you could set up a distillation so that C was getting distilled away over time. So you could decrease the concentration of C, and that also would shift the equilibrium, reestablish the equilibrium to the right. So there's lots of different options. You could have also decreased the concentration of D if C was the one that you were looking for. It just depends. The other thing is, what if D was what you wanted and it was also a liquid? You could distill that away and collect the liquid over time by distillation. So there's lots of different ways that you can do it. Okay, so what you'll notice also is that I've now related KEQ, favoring the products, to delta G. So there's a favoring the products means a negative delta G. That's what we saw in that previous slide. Okay, but I also want you to recognize that when we were looking at these energy coordinate diagrams, delta G wasn't mentioned over here. We did see delta H. So I want to relate how delta G and delta H are related to each other. And I need to go back and look at the formula. Delta G is equal to delta H minus T delta S. Oh my gosh. Okay. So what does all this mean? Well, delta S, if you recall, is entropy. Okay. And delta H is enthalpy. Okay, and delta G is Gibbs standard free energy. All right, how do I relate delta G and delta H? Well, delta S, this is some good news for you, the entropy, how that's defined in these reactions is that it's the freedom of motion of the products minus the freedom of motion of the reactants. So if you just think about it relative to making something more or less organized. If you're taking two different components, you're taking something A and something B, two completely different components, and you're trying to organize them and structure them to put them together into one molecule, your delta S will be negative. But if you have one molecule and you're breaking it apart into two different species, you're kind of, you're increasing the disorganization, then your entropy will increase, right? Entropy is sort of like this disarray, increasing randomness. When you're trying to take randomness and put it together into something more organized, that's going to be your negative delta S. You have negative entropy. Now, the good news, why bring this up? I just want you to be reminded of what entropy is, and that, yeah, okay, we are organizing and disorganizing, bond making, bond breaking, and such. But when you actually do the delta S values for these reactions, it is practically zero. It's so small that it may as well be zero. Okay, so that's the good news. So if delta S is practically zero, this whole delta S times T, temperature, gets canceled out. And if it gets canceled out, then all we need to know is this. The relationship between delta G and delta H is equivalent. They're practically the same. So when you know delta G, you know delta H. Not in numerical terms, but just in relative relationships, right? So an exothermic reaction is one where heat is given off, and you're going to have a delta H of a negative. If you have an endothermic, endo meaning inside, taking in, exo meaning outside, right? Exo is giving off heat. Endo means taking in heat. Think about exoskeleton and endoskeleton. So if you're taking in heat, then you're going to be a plus enthalpy, a positive change in enthalpy. This relates exactly to free energy. Exergonic, or outside, has a negative delta G. Endergonic, inside, has a positive delta G. So if we go back, a reaction that's favoring the products has a KEQ greater than 1, and therefore has a negative delta G, which means it has a negative delta H. Okay, so I've got you reminding that up here. Let's go back to our chlorination of methane. Now, I'm giving you these numbers, right? You can't just pluck these out of thin air. I'm giving you these numbers. These are all determined experimentally. The KEQ for the chlorination of methane is 1.1 times 10 to the 9. Okay, so you have a number that's greater than 1, so I know that the reaction favors the products. So for this reaction, in this equilibrium reaction, it's favoring the products. And look at the number, it's huge. So the delta G for the chlorination of methane, I know that if the KEQ is greater than 1, the delta G is negative. And look, experimentally, I'm telling you that the delta G is negative 108.7 kilojoules per mole. Therefore, chlorination of methane is favored. Or you could say it's exergonic, right? It's a negative delta G. The delta H for the chlorination of methane is negative 105.1 kilojoules per mole. Notice that they're not exactly numerically the same, but they're pretty darn close. So for all intents and purposes, they're about the same, right? Therefore, if I know the delta G is negative and I know the delta H is negative, and I can see that numerically that is the case, this reaction is exothermic. And that's because I've given you the numbers. A negative delta G value indicates an, I already wrote it above, exergonic reaction, or a decrease of energy. Okay, so I could give you all these numbers, and these numbers are kind of hard to put into your head. And that's the reason why we use energy diagrams. Let's take a look at this, right? You can see that we're starting at a given energy. And we end at a given energy. So we went from a high energy down to, I want you to look at this overall, from from this energy down to the final energy point, it says delta H is negative 105. There's a drop. From where I start to where I finish, there's a drop, a negative 105 difference in delta H. Okay? So that's how it relates to the y-axis. You can see that from start to finish, there's a drop. Thus, it's a negative. Take a look at these diagrams down below. Let's do a little practice. Let's look at A. Okay, so we're looking at the energy diagram on the left for a given reaction. How many transition states does A have? Hopefully you just said 1. Here's the transition state energy right up there. Okay, how many intermediates for A, for the reaction of from start to finish in A? Intermediates. In this case, 0. There are 0 intermediates. It went directly without forming a radical or carbocation or an anion. It just went from reactants to products. It transitions over the high energy state, transition state. Okay. Is the reaction going up in energy overall or going down in energy overall? And you can see here the reactants drop to the products. So it's a negative delta G, right? The delta G is negative. So it's exergonic and the reaction is favored thermodynamically. Let's look at B. B also has 1 transition state. It also does not have any intermediates. And if you look at the delta G for this reaction from start to finish, I go up in energy. It is a positive delta G. The reaction is not favored and it is endergonic. So these are just 2 examples of energy diagrams and how you can read them. So understand that I could have drawn, if I'm just talking about thermodynamics in a reaction coordinate. If I only am talking about thermodynamics, I only need to draw the starting material and the products and any intermediates, if there are any, I would draw an intermediate. So understand that you're only looking at the levels, right? The energy levels for all of these stable states, for these even intermediates. You're looking at the relative energy levels. Thermodynamics is all about where you started with, where you finished, maybe where you stopped in the middle. It is not looking at the trace of the hump. It is not looking at that transition. Okay? Thermodynamics is all about the energy you started with and the energy you finished with. If I want to talk about those lines with the transition states, I need to start talking about kinetics. That is when we start shifting towards a kinetic talk. So these energy coordinate diagrams, they house both thermodynamic information and kinetic information, right? The thermodynamics is all about, thermodynamics is all about the energy levels of these states, while the kinetics is all about the journey. How did it get from start to intermediate and intermediate to product? Okay, the kinetics is the how fast. How did it do that? So the how fast something is formed, we need to look at activation energies. Okay, and these are the energies between different starting points or ending points. So you can see that here, the EA, the activation energy from the starting material to the transition, the high energy transition state, that's your activation energy. And we can measure those, again, experimentally. They have to be given to you. You're not going to just pull these numbers out of thin air. And these are the things that you're considering in a reaction, in a chemical reaction. You can go back to the Arrhenius equation, where you're looking at the rate of the reaction, and you're considering a frequency factor, which is A, the activation energy, EA, the gas constant, and the temperature. Okay, and that's where that's how they're calculated. And an easier way to think about rate of a reaction, the how fast, is dependent upon a few things. You have to consider the number of collisions per unit of time. So if these molecules are in a solution, they're colliding with each other, and you have to consider those collisions. You have to consider the energy. Collision has to be forceful enough to get something to interact. And also you have to consider the orientation of the molecule, right? If you have a big molecule and one end of the molecule is partially positive and the other end is partially negative, if you have another molecule where one of its ends is partially positive, these two are not going to interact with each other because you have the positive ends going together. Remember, opposites attract. So the molecules have to collide in just the right orientations, right? The part of the molecule that's reactive to the other molecule that's reactive, where they're attracted to one another, it has to align. Everything has to align. So it's not just about randomly colliding into one another. You have to collide in just the right way. So how do we, as a person in the laboratory, how can we affect the rate of a reaction, given that rate takes these three things into consideration? Well, energy, how do we control energy in a lab? We do that with temperature. So sometimes we can get kinetics changed in a reaction if we raise or lower the temperature. Number of collisions and hoping that they're hitting in the right orientation. Number of collisions is going to ramp up if we do the temperature as well, because there'll be more motion, right? So they'll probably collide. Their temperature is going to affect the energy that they collide, but also hopefully more collisions because the number of collisions per unit time might increase. Also, dilution. We can increase the probability of collisions if the molecules are packed tighter together, right? So it's one thing if you have two people in a swimming pool and you hope that they interact versus two people in the Atlantic Ocean might never see each other, right? And so if you have a very dilute solution, the molecules are never going to find one another. But if you make it concentrated, now their collisions are increased per unit time and they're going to collide with one another. So we do have some control in the lab of improving kinetics. Okay, so from a diagram perspective, there's a couple different ways that kinetics can be manipulated. And I've already mentioned one of them. So if I, let's say, started with some reaction shown on the left here, where this is energy and this is the reaction coordinate. Starting material is here, intermediate, and product, let's say. Okay, so for this reaction, I have a couple different examples to show you how the kinetics can change for the same reaction. So to improve kinetics, I could add a catalyst. Okay, notice that the rate determining step is the first step from starting material to intermediate. It's the highest peak. So I could probably use a catalyst, and I'm going to show you in B how this doesn't change my starting material, intermediate, or product energies, but what it does is it lowers the highest energy peak. So now I don't have as high of a mountain to climb. I've lowered that. So I could use a catalyst to do that. That will improve kinetics, right? The reaction might go faster if I add a catalyst. Or I could destabilize the starting material, meaning I could do something to the starting material or start with a different starting material. So instead of the starting material being here, I change my starting material into a different species. so that it's higher in energy. So I start with something much less stable. And then I don't have such a big hill to climb, right? Because I'm still going to climb the transition state to get to the intermediate. But so I get to the same point of the transition state, but I've lowered the activation energy by destabilizing my starting material. So those are two ways on an energy diagram you can represent changing the kinetics of a reaction. Okay, here's an energy diagram. Let's do a little practice together. Which step in this reaction, A to B, B to C, or C to D, has the greatest free energy of activation? Remember, I'm asking you about activation energy. Which has the highest activation energy? So what you have to do is you have to look at the difference, right? From A to the transition, or B to the transition, or C to the transition. There are 3 activation energies. This is different than the rate determining step. I'm asking which has the greatest free energy of activation. So the answer to this first question would be, it looks like A to B has the biggest or the greatest energy of activation. I'm going to skip a B for a moment and go to C. Which step is the reaction's rate determining step? This is where you stand back and you look at all the mountains. And the highest mountain to climb is the one that is really, because that is the highest energy of the whole system. And you've got to put that much energy in. So the rate determining step is actually the one from B to C, because that transition state is the rate determining step. That's the highest energy peak in the whole diagram. So that's going to be the toughest one, because I have to put that much energy into the whole system in order to get over that hump. But there's my bottleneck. Okay, let's go back to B. Is the first formed intermediate more apt to revert to reactants or go on to form products? Well, let's look at something called the Hammond postulate in order to answer this question. And what the Hammond postulate states is that related species that are closer in energy are also closer in structure. So the structure of the transition state resembles the structure of the closest stable species. So let's take a look at that. If we look at the products for the example on the left, look at the products, okay? Notice that it is very close to the transition state. So the products is very close in structure to the transition state. In the example on the right, you'll see that the reactants are closer to the transition state energy. And so the reactants resemble the transition state more in the case on the right-hand side. Okay? So therefore, is the first formed intermediate is B, right? The first formed intermediate is B. Is B more apt to go to C, or is it more apt to go to A? Is it more apt to revert to the reactants, which is A, go back to A, or go on to form products? It has to go to C and ultimately to form products. So in which direction is it likely to go? And if you look at its relationship to its transition state, B looks more like energy-wise to transition state. We'll call it I. We'll call this one 2. 2I, and 3I. These are the transition states. B looks more like I as in 1, than 2 relative energies, according to Hammond postulate. Therefore, it's more likely to revert back to A than go forward to C. And that makes sense too, because the rate determining step is also the second one. So the answer would be revert back to the reactants. Okay, so we have unpacked what information is given in an energy diagram, okay? So I want you to be aware of the delta H differences from start to finish, or how that relates to delta G, right? Energy differences from start to finish. How many intermediates are given on an energy diagram that speak to the mechanism? How many transition states, therefore? These are all things that you can pull out of an energy diagram. But again, I just want to remind you that you need to be given the values and the relative exergonic, endergonic, or enthalpies. Those you can't just decide for yourself. Those are determined experimentally. Okay, so just a reminder that all values, right, the delta H, the delta G, these are determined experimentally. But they're expressed very succinctly in these energy coordinate diagrams. Okay, we've been staring for a long time now at the energy coordinate diagram for methane radical halogenation. Let's go back to that more complicated example. I showed you that you could get possibly 2 different constitutional isomers for propane and bromination. Now, I want you to understand that kinetics and thermodynamics do not play along with statistics. What does that mean? Well, I once showed this problem to a mathematician, and they said, with minimal understanding of chemistry, I asked them to predict which one would be more prevalent, 2-bromo or 1-bromo propane. And they looked at it from a statistical standpoint and said, okay, you just showed me all this kinetic stuff, right, with collisions and whatnot, and you've got 6 hydrogens on the ends, and you've only got 2 hydrogens in the middle. And I saw your mechanism, and it looks from a probability standpoint, from a collision standpoint, you're more likely to get the ones on the end because there's 6 opportunities to pull off those hydrogens and put a radical there versus the 2 in the middle. And that is not what we see, right? Because if that were the case, 6 primary hydrogens, right, the 6 of them in blue here, versus the 2 secondary ones, 2 secondary hydrogens, that does not work out, okay? And so what we end up seeing is something else going on here. So you can't just look at statistics and kinetics alone. You've got to combine it. So there is a major difference, and we can understand it a little bit better when we look at the energy diagram. And given experimentally the energy diagram, if you look at the starting material, here is the propane, right? And the bromine radical. These are the intermediates. Okay, it's not showing you the products are over here somewhere, but they're not showing you, they're only showing you the first half, which happens to be the rate determining step. This is from starting material to the intermediates is the rate determining step for this reaction. And what you'll notice is that formation of the secondary radical is lower in energy and takes less energy to get to versus the primary radical. Look at the energy difference. There's a 13 kilojoule energy difference between the primary radical and the secondary radical? Let's investigate that. Here's our qualitative description. And this is the type of thing that we were doing with REO, right? We're qualitatively analyzing stability. So here's the trend that I'm going to show you. If you have a carbon with a radical on it, think about what that means, okay? A carbon with a radical has 3 bonds and 1 electron. So it has 7 electrons, right? It wants 8, octet. So ultimately, there's a relationship, right? Like with the carbocation, it is in need. It wants more, okay? It only needs a little bit more and it just wants more. So if I have 3 R groups mean alkyl groups. Methyl, ethyl, butyl, those types of things. So remember what I said about like something like a CH3. By induction, we considered it to be a weak but nevertheless electron donating group. That's kind of good. It's not resonance, but man, electron donating group. If I have 3 electron donating groups, electron donating group, electron donating group, electron donating group, I am making that radical carbon, the one, the one that wants more, feel so much better. So if I have 3, or otherwise known as a tertiary radical, that is going to be more stable than a secondary radical who has 2 electron donating groups next to it, which is more stable than a primary radical. That's just one friend giving you a little electron density. And it's more stable than a methyl, which has nothing, just hydrogens around it. That's the least stable. You can rationalize that by induction. We want donating groups to stabilize a radical. And look at the relative rates of radical formation by a bromine radical. A tertiary carbon radical is 1,600 times faster than a secondary than a primary, right? We're looking at relative rates here. Why? Because of the stability of the intermediate, the high energy intermediate that you're making. Now, let's bring it all together. Remember, we just looked at the radicals. Radicals are carbons that want more. So tertiary is better than secondary, is better than primary. Remember a carbocation? A carbocation is a carbon with 3 bonds, no lone pairs, no one, right? No one electron. And man, a carbocation doesn't want just 1 electron. It's in need of more, right? It wants more electrons. It wants 2 more electrons to share. So look at the trend for a carbocation and a radical. They have the same trend. Tertiary, because having more electron donating groups around you, is better than secondary, is better than primary, is better than methyl. So I want you to group these electron deficient compounds together, right? So whenever you form an intermediate, whenever your mechanism gives you an intermediate with a carbocation or a radical, you already know thermodynamically that those intermediates will be lower in energy if they're tertiary versus if they're secondary versus if they're primary. A carbanion, on the other hand, right? Think about a carbanion. A carbanion, this is what we were looking at, right? We used REO. We used REO to look at the negative charge left behind. Okay, so whenever you're left with an intermediate that has a negative charge, you're going to use REO to figure out its stability. And when you get to induction, if you get to induction, notice that a carbon minus does not want, right? It wants to offload. So it would prefer having electron withdrawing groups, not electron donating groups. So if the R group surrounding, if the groups surrounding the carbon, our R's are all donating groups, the fewer the better. That's why a CH3 minus is way better than a T-butyl. You don't want donating groups donating more electron density to a carbon that's already got too much. Okay, so you see the reverse trend for a carbanion. You don't want a tertiary carbanion. It wants fewer donating groups. Pictorially, this inductive effect can be explained a little bit better. Think about a carbon, right? Let's say it has 2 hydrogens off of it, and it's a carbanion, so carbocation. So remember that if I had a CH3 off of it, we're saying things like, oh, it's electron donating group mildly. A better way to understand what's really happening here is through hyperconjugation. So here I have a trigonal planar carbocation. And so you can see this blue p unhybridized p orbital. And what's happening is that you've got the tetrahedral, right? You've got the tetrahedral bonds to the CH3. And though they're not perfectly aligned, obviously, if they were perfectly aligned, they'd be sharing electrons and forming a bond. But the tetrahedral sp3 orbital and the p orbital of your carbocation have a weak overlap. And it's the electrons that are in that bond, the sp3 orbital bond with the hydrogen, that lend a little electron density. It's just, I consider hyperconjugation like the hug, right? Resonance is when you have a carbon plus and your friend next door, because you're allylic, your friend next door has electrons. Like you're in need and your friend next door is like, I'll help you out. Here you go. Resonance is more powerful, right? Your friend helped you out and now they're without. Now they have a hole in their pocket. In hyperconjugation, you don't have actual giving of electrons, nor do you actually have a bond there, but it's just like having a friend nearby to support you. You can feel their presence. You can feel the presence of the electrons in that bond, and it's close enough that it makes you feel more stable. And so this hyperconjugation, this weak overlap, very weak, not enough to make a bond, is enough to stabilize the empty p orbital. And that's just with one CH3. Put another CH3 here or here, and you have more and more hyperconjugation. So the more and more friends you have around you making you feel better, it'll be okay, right? When you're lacking electrons, the more friends you have around you, not actually giving you electrons like resonance, but helping you out, donating their support. This is your electron donating effect. How else can molecules, reactive intermediates, be stabilized? Well, we already talked about that. Resonance is a big one. Resonance and inductive effects are huge. If your intermediate is negative, use Ario to figure out stability of that negative charge. If your intermediate is positive or a radical, consider resonance first, because having your friend actually give you electrons is really good. And then you can consider hyperconjugation or inductive effects. This brings us to overall view of how to relatively rank these carbocations and their radicals. And you can see it's the same trend. Okay, relative stabilities of carbon anions, I just said it, use Ario. You know how to do that. It's a great protocol. Carbocations and radicals, again, they have a trend. Tertiary is awesome. Notice that they have the same trend. Tertiary carbocation, tertiary radical. Followed by, this is primary, okay, but This is a primary but. Primary but. Check out the resonance. Whoa, it's got a benzene ring next door, and there's a lot of resonance contributors you can write for that. So it's primary, but it has a lot of resonance contribution. This is notice that it's about the same, not greater than, it's about the same as just straight up one resonance structure, right? Next door, it's allylic. These are allylic, but primary but allylic. And that is roughly the same as secondary. So resonance stabilization and secondary are, as long as the resonance is, about as primary with resonance, then you've got about equal energy as a secondary. Secondary is better than primary, and primary is better than methyl, and methyl is even better than vinyl. So that's a trend to get used to relative to inductive effects. You are now armed with a lot of power. Why? Because when you're looking at an energy diagram, if you can understand the thermodynamics of whether something is going to be more stable, lower in energy, or less stable, higher in energy, you're starting to qualitatively map out the energy diagram. And if you're armed with the mechanism, then you know whether there's intermediates or not. So I want you to be able to write the complete mechanism for a halogenation reaction on any alkane. I want you to be able to dissect the meanings that come out of an energy diagram, right? Identify transition states, identify energy of activation, describe the energies of different reactions relative to delta G and delta H, identify the rate determining step if you're given the energy coordinate diagram, qualitatively justify reactive intermediate trends. Why is that intermediate more or less stable than some other intermediate? Okay, and I want you to be familiar with these terms. I leave you with a bunch of practice to try out your skills.